Okay, yeah, so let's get started. So I'm going to be presenting this paper titled Theoretical Analysis of Self-Training with Deep Networks on Unlabeled Data. This paper comes out of Stanford University, and I think it'll show up in iClear here in like the next month or so. The authors are Colin, Kendrick, Shen, Yining, Chen, and Tengyu. And essentially what this paper provides us with is a framework with which we can think about these topics of unsupervised learning, domain adaptation, and self-training, specifically in the context of deep neural networks. So first I'll build the context a little bit for the problem. I'll define the setting, and then we'll go over these key assumptions that the paper makes, which are pretty interesting and I think fairly intuitive. And then I'll provide two population guarantees, one for the unsupervised setting and one for the setting of self-training. And then I'll provide the finite sample guarantees, which are derived using a lot of the techniques we've seen in class. So I think that's pretty interesting. And then I'll talk about their experiments and then briefly talk about some discussion that I saw on open review, depending on how much time we have. So first, to build the context a little bit. So, we've spent the last few weeks in class here talking about this setting where we really don't have as much labeled training data as we would like in order to be able to learn a good model. So we've looked at these recent large language models that train on some large unlabeled data set using like a masked word prediction task. And then we can take this model and we can apply it to some more specific downstream task by fine-tuning it with a smaller labeled data set. We've also looked at contrastive learning, which is a form of representation learning, where the model learns relevant features in an unsupervised way by comparing unlabeled examples. And then finally, we've taken a look at this notion of weakly supervised learning, which is technically a form of supervised learning, but it's very relevant for our context where we have some maybe weak classifier that was either trained in a different domain or trained with a small labeled data set. And we'd like to use it for generating noisy labels for our otherwise unlabeled data. And then we can use that to train another, hopefully better classifier. And so what this paper provides is some theoretical framework with which we can think about these problems, specifically a framework that applies to deep networks. So I think we're pretty familiar with the unsupervised setting, so I won't spend too much time building the context for it. However, I would like to spend a little bit of time building the context for self-training. So when we talk about self-training in the context of this paper, what we're really talking about is the situation where we have some weak classifier. As I said, maybe it was trained for a different domain, or maybe it was trained on just a very small labeled data set. And we also have this very large amount of unlabeled data that we'd like to use. So what we'll do is we'll use this weak classifier to label our unlabeled data, and then we'll use that to train a new classifier that hopefully performs better. And so you can also think of this as this like student-teacher paradigm, where the weak classifier is the teacher and it's teaching a new student classifier. So specifically, we'll start out with this weak classifier. Maybe it doesn't perform so well. And we'll have it provide us with some noisy labels on our unlabeled data set. We refer to these as pseudo labels. And then we'll combine this pseudo labeled data set along with our labeled data set, and we'll retrain a new classifier. And again, hopefully this new classifier outperforms the weak classifier that we started with. And of course, the interesting thing or the useful thing about this student or this teacher-student paradigm is that we can choose to iterate this process multiple times, where hopefully we can improve upon the classifier with each iteration. So is this clear as far as like a setting goes for this self-training? Because this is kind of the most important building block for what we'll be talking about.
Step 2, just use the classifier from step 1 and generate the pseudo label, right?
Yep, that's it. And then you just retrain a new classifier with it. It's not too complicated.
Got it.
So.
Thanks.
And to further motivate this paper, I'll note that there have been some recent successes in self-training. Specifically, good results have been shown using self-training along with this notion of input consistency regularization, which essentially means that we enforce consistency of predictions under transformations of the unlabeled data. So these transformations can take the form of like adversarial perturbations or like more normal data augmentation or noise. And so what these, to be more specific, what these papers have shown is that these techniques can achieve accuracy that's pretty comparable to supervised learning, but they can do so with a very small amount of the labeled data. And so the results down here are for this noisy student model, which was published last year. And they were able to, the authors were able to dramatically improve upon ImageNet accuracy by using 300 million unlabeled images. And they improved by about 2% over the previous state of the art. And the previous state of the art used about 3.5 billion weekly labeled images. And so they're using significantly less unlabeled data to get better results. And that's attributed to this notion of input consistency regularization. And I will also note that I took a look at the benchmark when I was writing up the presentation. And I think the current state of the art is around 90%. So it's even a couple percent better than this. And I didn't look at the details, but I did note that the title of it has something about pseudo labels. So presumably it's also along this line of work.
So I just want to make a quick note. Yeah, that was amazing. So that 90% result came out, I think, later last year. It was like big news on Twitter, and I think it's a combo of the self-training plus contrastive learning. So
okay.
Curious. Yeah.
Definitely we'll have to take a look at it later. But yeah, so this essentially this paper that we'll talk about provides some theoretical explanation for the benefit of using input consistency regularization in this context. So in fact, input consistency regularization is one of the key assumptions that's made in this paper, and we'll see it shortly. So now I'll go over these key assumptions that are pretty interesting. The first of these is this notion of expansion, which intuitively is some notion of how the underlying class conditional distribution is connected in input space. So on the next slide, I have like some diagrams, and I'll talk through it a little bit more, and hopefully that will help clarify it. And the second one is this input consistency that we just talked about, which essentially is some notion of how the ground truth classes are separated in the input space. So if you combine these notions of expansion, where a class conditional distribution is connected, along with some notion of how they're separated from other classes, then you can combine those and get some notion of how we can learn with that information, right? So expansion, as I mentioned before, is this notion that our underlying class conditional distribution is connected in input space. So as an example, we can consider like this manifold of some particular class conditional distribution. In this case, we'll say it's like the points that are dog points, and or have some probability of being dog. And then expansion states that for all sufficiently small subsets V, the neighborhood of V has to be sufficiently large. And so the paper talks about some specific definitions of neighborhood and of sufficiently large, but they also note that the findings here may be applicable to other definitions. We'll give the specific ones though, just to help us think through it. And for now, just consider a neighborhood as being like some L2 distance away from a set of points. So in this example, if we select this like small island down here in the lower right as our set V, then what we'd like to see is that if we look at the neighborhood of V, which is this orange section, that it's expanding into some additional probability mass of our class conditional distribution. But in this case, it doesn't. So we would say that this does not satisfy expansion because it's expanding into points that are not, they don't have any chance of being dog. So we're not increasing our probability mass at all, right? They might be cat points or something like that. So this does not satisfy expansion. However, if we look at a slightly modified version of the class conditional distribution, where it's got this connection that's bridging the sort of mainland with this small island. And if we look at the neighborhood again, we would say that this does satisfy expansion. And the reason is because we're adding some amount of dog points along this connection here, right? And so I just want to note that for expansion to actually hold, it has to hold for all subsets V under a certain size. So it's not just this one subset, but it has to hold for all of them. However, you know, it can be noted that this, because it's connected, like at all, then it will satisfy this notion of expansion in this case. But on the next slide, I'll show the more formal definition. So the authors give a few different, like specifically, the authors give 3 different definitions of expansion. The other 2 are used exclusively in the proofs, and so I won't go into them in too much detail. The one that we're talking about here is called multiplicative expansion. And so in this case, so in this left term here, P sub I is the class conditional distribution for some class. And N of V is the neighborhood of our set of points of V. And so this left term is essentially the class conditional probability mass of the neighborhood of the set V, right? And so for multiplicative expansion to be satisfied, this probability mass has to be greater than some multiplicative factor C times the probability mass of the original set V, right? And so the second inequality here is what I mentioned on the last slide, where it has to be satisfied for all sets V that are less than or equal to some size limit A. And specifically for unsupervised learning, what we require is that A is equal to 1/2 and C, this multiplicative factor, is greater than 1. And so what we're saying when we say that the distribution must satisfy this is we're saying that there can't be these separated pockets of the same class conditional distribution in our input space. Like there can't be those islands that we saw before. And you can see this because if we imagine a set V that is precisely half the class's probability mass, then because it must expand by at least some tiny amount, if C is greater than 1, then the probability mass that it's expanding into is the other half of the probability mass. And that probability mass also has to satisfy expansion. And so essentially what we're saying is it has to be connected in input space. Is that pretty clear? And yeah, we'll have a different notion of expansion, or we'll have different expansion requirements for the semi-supervised case. That's only for the unsupervised case.
So this expansion is for a distribution or for a for B. Yeah.
Yeah. So the notion of expansion has to be satisfied for the underlying distribution. We're not looking at the empirical distribution. I should have noted that first of all. We're looking at the underlying distribution, right? And in order for the underlying distribution to satisfy expansion, each of the class conditional distributions have to satisfy expansion. So it's really defined in terms of the class conditional distribution, but if all of the class conditional distributions satisfy it, then the overall distribution satisfies it.
Yeah, thanks. Makes sense.
Yep. So I'll be a little more precise here about the neighborhood of X, or the neighborhood of a point. So imagine we have this blue point here, we'll call it X, and we will take a look at all of the data augmentations of this point X. So, I mean, imagine any data augmentation you want. Maybe you're like rotating the image or adding some noise or whatever. We look at all the possible data augmentations of this point X, and then we look at some L2 distance away from those, okay? And that set is called this transformation set of X. And we'll use this notion a lot. So remember this notion of the transformation set of X, and we represent it as B of X. So look at the transformation set of X, then pick another point, call it X prime. Look at the transformation set of X prime. And if the transformation sets of X and X prime overlap, then they're considered neighbors, okay? And so if we're talking about the neighborhood of X, we do this for all possible X primes, and we collect all of those points that are neighbors of X, and then that becomes the neighborhood of X. Does that make sense?
What kind of transformation are we considering? Like, or is that, yeah, to be given?
Yeah, so we don't really define more specific data transformations, but they can be, I think, kind of anything you want, right? So you could like be coloring an image to a different color, adding noise. And one really important one is adversarial perturbations. So those can also be considered as data augmentations or data transformations of X. So it's really kind of anything you want to imagine. I think of this later as almost like a hyperparameter, because, and I'll talk about this a little bit in one of these slides, but if you change what transformations you're using to augment your data, you can affect the size of the neighborhood. So if you add more data augmentations, you actually increase the neighborhood. And so that has some effects that we'll see in some of the population results.
Got it. Yeah.
And then of course, it's super natural to extend this to this notion of neighborhood to a set of points. It's just the union of the neighborhood of each of the points. So you just combine them together, right? And so in the paper, the authors give two examples of this expansion with respect to some specific distributions. So as I mentioned, this notion of expansion has to be satisfied for the underlying distribution, right? And so we'll talk about it again later too, but it's difficult to show expansion empirically because it's a property of the underlying expansion, but the authors are the underlying distribution, but the authors want to give some examples of some realistic distributions that do satisfy, that they can show satisfy expansion. And so the one they give here is this mixture of Gaussians, where each class conditional distribution is Gaussian with mean tau I and isotropic covariance. Isotropic covariance just means that the Gaussians are spherical in shape. And the dimensionality of these Gaussians is defined to be greater than the number of classes, which is K. And our transformation set, in this case, they're choosing not to add any data augmentations. So they're limiting our transformation set only to the points that are some L2 distance away from our chosen X, right? So that's just sort of like I said, they're choosing to limit the neighborhood in this way. And I won't go into the details here, but they're essentially able to show that this satisfies 0.5, 1.5 expansion. And the two numbers here are the A and the C that we saw from multiplicative expansion. So in this case, A equals 1/2 and C would equal 1.5. And so this would satisfy AC expansion, the AC expansion requirement, the multiplicative expansion requirement for unsupervised learning. And so essentially with low error, they would be able to recover this mixture of Gaussians. And so really the authors are just giving this as an example of a realistic distribution. I mean, this is just Gaussians that satisfies AC expansion. One other thing they note is that, like I said before, this is a property, expansion is a property of the underlying distribution. And so it's satisfied in this case. However, if we look at the empirical distribution, it does not satisfy expansion. And the reason for that is that if we sample 2 points from one of these Gaussians, the distance between the points is lower bounded by 1 with a high probability. And the reason for that is because of our choice of this covariance matrix of being 1 over D, essentially. And so because it's lower bounded by 1, and because we've chosen our neighborhood size to be defined with respect to this transformation set and to this L2 distance of 1 over 2 root D, that's much smaller than 1. And so these 2 points that we've sampled with high likelihood will not be neighbors of one another. And so again, they're just saying that expansion needs to be satisfied for the underlying distribution, but in practice, it may not be satisfied for the empirical distribution. And so they give a second example, which again, I won't go into too much detail here, but essentially we have these QIs that are generator functions that map from a random vector Z in D space up to some higher dimensional vector in D prime space. So D prime is greater than D. And essentially, we have one of these QIs for each of the classes. And the only requirement for QI is that it's kappa by Lipschitz, which is essentially like this. It's like Lipschitz, but it also has this lower bound, which is 1 over the Lipschitz number. Essentially what the authors say here is that, so this also will satisfy 0.5, 1.5 expansion. And they show this by essentially reducing it to the Gaussian case and then using the same proof that they used for example 1. You know, I had a little bit of difficulty gaining a ton of intuition from this, but essentially the intuition that we figure we gain from this is just that this is a pretty complicated function. Like these QIs are pretty open, like, and you're also mapping from a lower dimensional space to a higher dimensional space, right? So you can get like a lot of mixing of these distributions, but they're saying that even when you do this, you can still recover in an unsupervised setting. You could still recover these clusters or these distributions. Okay, so the second assumption, which is the one we talked about near the beginning of the talk, was this notion of input consistency. So essentially, what we ask when we're talking about input consistency is when we're given a point X, if we look at the transformation set of this point X, do the labels of these points match the label of X? And so specifically what we have here is the population consistency loss. That's what the definition is here, this R sub B of G. The B here refers to our transformation set, and G is going to be whatever classifier we're considering. It's defined as the fraction of points for which that point's transformation set contains a point that is labeled inconsistently, right? And so it's just the expected value over the population of this indicator random variable, which is 1 if there exists an X prime element of our transformation set such that the labels are different, right? And so this is this notion of being robust to input transformations. So if we look at a point X and we say X is robust to input transformations, what that means is that all of the points in the transformation set of X are the same label as X. And so that's desirable. And you know, another way to think about this is if we pick the set of points belonging to a particular ground truth label, and if we look at the transformation set of this set of points, then if this set is robust, then that means that there's no neighbors to this set that are of a different ground truth label. And so this gives some notion of how different classes can be separated from one another. And obviously, if they're well separated, then it's you know, easier to learn. And so in the context of this paper, we'll always retain this this requirement, this assumption that the fraction of points that aren't robust to input transformations, this R sub B of G, is bounded above by some mu. And we'll see this in our guarantees. Okay, so now we'll take a look at the first guarantee, which is in the unsupervised setting. So first we'll present this the unsupervised learning objective that we use to train a classifier G. We simply minimize this notion of input consistency loss with respect to G. So in other words, what we're doing is we're maximizing the fraction of points that are robust to input transformations, right? So we're maximizing the fraction of points whose transformation sets have the same label as our point that we're assessing. And we also have this additional requirement, which essentially, so Y is drawn from our set K of possible labels. And so this additional requirement says that the fraction of points that are labeled as any particular class is greater than the input consistency loss. And so the way I interpret this, and the paper doesn't talk about this, but I interpret this to be saying that we don't want to ignore some low probability class. Like if we only have like 2% of our points are dog points, then it might be worth it for us to just ignore these points and then minimize our loss ignoring them. But here we're saying that the fraction of points that are labeled as dog has to at least be as much as what our loss is. So that's my understanding of this additional requirement, is we're trying to not ignore like low probability classes. And so here we have our result. So if we have some G hat that minimizes the objective we just looked at, and if we satisfy AC expansion with the required 1/2 for A and C greater than 1, as we talked about, and if we also have this population input consistency requirement where it's bounded by mu, and then this last requirement is the same as what we saw on the other slide in the objective where we are making sure that we consider these low probability classes, then we end up with this this bound on our unsupervised error of our minimizer G hat. And you can see that this bound is affected by two quantities, C and mu. And so if C, our expansion factor is greater than or equal to 2, then we end up with this bound of 2 mu. Whereas if C is between 1 and 2, then it's larger than that. And of course, as C approaches 1, this bound kind of blows up, right? And so this makes sense because, you know, if we satisfy expansion with a larger expansion factor, then you know, it's easier to learn essentially, and because they have larger neighborhoods, right? And so this is what I spoke about before. The authors also note here that a larger neighborhood and thus a larger expansion factor C can be intentionally induced by increasing the amount of data augmentation that we use. And so they pose that this may be an explanation for some recent findings in the SimClear paper, that more aggressive data augmentation results in better results in their setting of unsupervised contrastive learning. And then of course, we also have this mu term, which is the upper bound on the input consistency, the population input consistency loss of our ground truth classifier. And so it makes sense because we're saying that the fraction of points that are not robust to input transformations is small, right? So if there's good separation, then this mu will be small and our error will be small as well.
Matthew, so
yeah.
For the restriction that the probability of the smallest class is like lower bounded by that quantity, like that restriction is given, or are we optimizing with respect, like, okay, yeah, I guess we can't optimize. Yeah, it's like
yeah, it's just like a restriction, I guess, on our learning objective, right? So in addition to minimizing our input consistency loss, we're also saying that this must hold. And again, in the paper, they don't give like a good explanation of why, but my best interpretation is that we're just trying to not ignore low probability classes.
And Is there an easy way to enforce that constraint? Or
I mean, in practice, honestly, I don't have a good idea off the top of my head.
Yeah, it just seems yeah, curious.
Yeah, I'm trying to think. I mean, I guess if we can calculate like the input consistency loss for our classifier. See, but yeah, so there's some discussion on Open Review too about some of the terms of these learning objectives. Specifically, they're defined in terms of an expectation over the population. And so they're difficult to actually calculate some of these in practice. The authors talk about like some analogous losses and things that can be used instead of these terms. But that's sort of one drawback, is that some of these terms and these objectives are defined in terms of the population, which is difficult to calculate in practice.
Right. Yeah. So these will be just used in the theoretical analysis. Huh? Yeah.
Right. Right. In the experiments, they use some of these analogous losses or these analogous techniques in order to provide like some evidence that these learning objectives are reasonable. But again, they're not like one-to-one. Like they're slightly, they're just analogous. They're like, similar.
It makes sense. Thank you.
So because of our limitation on time, and because I don't really think the proof is that interesting on a very granular level, we'll just kind of give a brief outline here. So there are essentially 3 steps. The first is that they show that there's like a similar population guarantee for a different kind of expansion, which is constant expansion. I won't talk about it, but it's similar to our notion of multiplicative expansion. It's just a similar assumption. And the second is to show that if you have multiplicative expansion, it implies that you also have constant expansion. And then there's just a few loose ends that they kind of have to tie together. So essentially, most of the reasoning here, or most of this proof, is reasoning about sets. It's like, this set intersected with another set is the complement of whatever. And so it's not necessarily like challenging in that way, but it's very complex, and I don't think it's worth going over. The one thing that was kind of interesting is that the authors are able to show through this reasoning that every cluster that's found by G, our classifier, will essentially like take up some majority label of some ground truth, the majority labels of some ground truth class. And so we're talking about unsupervised learning here. So really this is some notion of like clustering, right? And so what we're saying is, because they're connected together, the authors are able to show that with our assumptions that because they're connected, they'll take up some majority label essentially. So now I'll go over the population guarantee for our self-training setting. So in the case of so we have a different assumption here. So in the case of the unsupervised setting, we required multiplicative expansion with A equal to 1/2 and C greater than 1. For the self-training setting, our requirements are a little bit different. So in the self-training case, we have access to these pseudo labels, right? And these pseudo labels can give us information about the labels of various clusters that are found by our classifier. And so what this means is that the class conditional distributions don't actually have to be fully connected in input space. And so, you can see this because you can imagine, like, if we, in the unsupervised case, if we have 3 classes, but we have like 8 clusters of points, we don't know which label belongs to which. However, if we have 3 clusters and we have 3 classes, we know that there's at least some permutation that we can assign that's going to be pretty close to correct. However, in the case of having these pseudo labels, we can actually use the pseudo labels to help us classify these like disjoint clusters. So we actually don't require A to be 1/2. A can actually be smaller than that, right? Instead, what we require is that expansion holds on sets that are smaller than the size of the set of mistakes of our pseudo labeler. And so we define this set of mistakes as this M of GPL, where GPL is our pseudo labeler. And the idea here is that expansion, along with our input consistency assumption, will allow us to sort of outweigh these mistakenly pseudo-labeled examples. And so essentially what we end up doing is we end up denoising the mistakes of our pseudo-labeler. So formally, we require expansion on sets smaller than a bar, where a bar is the maximum fraction of examples in any class that are mistakenly pseudo-labeled. And we require this expansion to occur with an expansion factor C greater than 5. So this is much greater than our greater than 1 requirement for unsupervised learning. Now, of course, if we require expansion with a C of greater than 5, then we obviously can't satisfy that if a bar is greater than 1/5 of the probability mass, because our probability mass is 1. So we also require that a bar is less than 1/5. But so in summary, essentially, like we require A can be smaller in this case because we have these pseudo labels, but we need to have the extra expansion power to be able to outweigh our mistakes of our pseudo labeler. So here's the minimization objective for this self-training case. It looks pretty complicated, but essentially it's just a weighted combination of R sub B of G, which is the input consistency loss, and this 0,1 loss term, which is defined as the fraction of points for which our trained classifier G and our pseudo-labeler GPL disagree. So it's just a measure of the disagreement between our classifier and the pseudo-labeler. This error of GPL term is just a constant, and the authors essentially say here that the different weighting factors along with this error of GPL term that we see here are essentially just for they're just tailored for the analysis of the accuracy bound, but they don't necessarily like play a pivotal role in the analysis. So really all we're doing here is we're just minimizing the fraction of points that aren't robust to input transformations, while also minimizing the disagreement between our trained classifier and the pseudo-labeler. So again, here's the result. If we have some G hat that minimizes the previous objective, and if A bar C expansion holds with the requirements that we just talked about, and of course, we also have the population input consistency requirement where it's bounded by mu, as we talked about before. Then what we'll be able to say is that the error of G hat, our minimizer, is bounded by this expression here, which again is a combination of C and then also the error of our pseudo-labeler and mu. And so you can note that if expansion is satisfied very strongly with a high value of C, then the effect of the mistakenly pseudo-labeled examples can be small. And then of course we have this mu term, which is sort of like the inherent difficulty of, it's like the inherent like unseparatedness of our underlying distribution. And so that's we're always going to see this term. And so the benefit of this type of training, this self-training, is that we can apply this this teacher-student paradigm iteratively, and we can do this multiple times. So after iterating many times, the error bound approaches what's given here. And you can see that the mistakenly pseudo-labeled examples no longer affect the bound. Essentially, they've been denoised. And what we're left with is just this mu term multiplied by some other term that depends on our expansion factor C. So in the case that C is very large, this approaches 4 mu, which is the same as what the non-iterated bound would be. So for large values of C, it seems like it doesn't really matter too much whether you iterate or not. However, if C is pretty low, like let's say C is equal to 6, and we require C to be 5, but let's just say it's 6, Then the non-iterated bound, you get 4/5 times the error of our pseudo labeler plus 4 mu. But in the iterated bound, you get 20 mu, right? And so you can see that there's like some trade-off here between minimizing the effects of the pseudo labels, the mistakes in the pseudo labels, versus magnifying sort of this like inherent inconsistency in the underlying distribution. And so, you know, in practice, I'm sure we could treat this as like another hyperparameter where you choose how many times to sort of iterate this teacher-student process, right? Hopefully mu is pretty small. So hopefully in practice, we would have to iterate many times before we see, you know, a detrimental effect from mu. But you know, it's an option here. And so again, the authors note that this result can explain some recent results. And so we talked about this noisy student model before. And the authors also note here that that in that paper, they were able to see this effect of iteratively applying self-training, improving performance pretty dramatically. And so the authors of this paper are able to show that with this result here. So again, the proof is, you know, fairly similar to the proof of the last population guarantee. There's another notion of expansion, which is this additive expansion. Again, I won't talk about it, but it's similar to multiplicative expansion. And you know, the interesting thing, I mean, again, this is all just like a lot of set reasoning essentially. But what they're able to show is that the error of our classifier is actually upper bounded by the objective, which I thought was kind of interesting. But essentially they're able to show that, and then they just apply our input consistency assumption that we've been using, and they just like replace a couple terms, and then bam, you have the same bound as what we just showed. So it's not too, it's complicated in that there's a lot of steps because it's a lot of reasoning about sets, but I don't think there's a whole lot that's like too interesting to look at. So now I'll try to quickly go over these finite sample guarantees that they provide. Specifically, what the authors are able to do is they're able to show that there are bounds on these three quantities. And these are the three quantities that really make up our objectives that we saw earlier. So once they show that these three quantities are bounded, they're able to essentially plug these into our population guarantees. And that will result in finite sample guarantees. And the one thing I'll note here is that our objectives are defined in terms of, you know, this is all applicable to deep neural networks. And so our objective functions are defined in terms of that, right? And because neural networks are parameterized, they're able to essentially just show these bounds on these terms and then convert it directly into finite sample guarantees that depend on the unlabeled data. So the proofs for these three terms are very similar. So we'll just look at the top one, our input consistency loss. The bounds look similar, like they look very similar, and the proofs are very similar. So we'll just look at the top one. So this is a very, very rough outline. I actually wish we had more time to go over some of the details of this because I think some of this is pretty interesting. But essentially, to begin, the authors introduced this notion of all layer margin. The idea here is to add some perturbation to each layer of the neural network in order to induce it to have a different label. And so the all layer margin is defined as the magnitude of the smallest perturbation required to flip the label. So it's kind of like asking, I mean, it makes sense that it's a margin because essentially what we're asking is how close is the neural network to changing its prediction, right? So like in terms of a normal margin, this is kind of what we would think about, but this is applicable to neural networks. And it can also be viewed as like some measure of the stability of the neural network. And then, so more specifically, they provide this notion of robust all layer margin, which is a slight extension where we look at the transformation set of a point X. And we ask the question, how close is the neural network to predicting a member of X's transformation set as a label different from X? And then again, the magnitude of the smallest perturbation required to do this is the all-layer margin, is the robust all-layer margin. And then essentially the authors are able to show that this robust all-layer margin is Lipschitz and F, where F is our neural network. And then we define our hypothesis class as the ramp loss, which we saw in class, which is just like a smoothed version of our 0-1 loss in order to make it Lipschitz. We compose that with the robust all-layer margin. We get our hypothesis class. And then they're able to use the Lipschitz, the fact that it's the ramp loss is Lipschitz, along with the fact that the margin is Lipschitz in F, in order to derive an epsilon cover. And here they use this notion of chaining that we talked about in class, where you use like progressively smaller epsilon covers in order to derive a tighter bound. So that gives us the Rademacher complexity. And then we just use our normal generalization bound using Rademacher complexity in order to get a bound that's defined in terms of the all-layer margin. And then there's just a little bit of bookkeeping here to sort of redefine this in terms of our input consistency loss. And then finally, there's, we get to use the union bound over this threshold because it's only defined for a single threshold. And so we divide it into a grid and then union bound over these choices. So I thought that was pretty interesting too. I highly recommend, I'm really not doing it justice here by going over it this quickly. So I highly recommend that you take a look at it. So I think we're getting pretty close to time here. So this is the result of the analysis. We have this bound on the input consistency loss. So again, I mentioned last time that the authors are able to show similar bounds for those other quantities that show up in the objectives. And the proofs of those are very similar. So you can see that this bound is determined by the fraction of points that have robust all-layer margin below some threshold t. Then we have this other term, which is this soft O term, which essentially just hides polylogarithmic factors. And it contains this Q, which actually is not defined in the context of these proofs. The only Q that I'm aware of in the paper relates to the other definitions of expansion that we didn't really talk about. So it might be this, but I really scoured the paper and was not able to find some other reference to this Q. It actually comes from a different paper of theirs. And so I didn't get to look into that in too much detail, but presumably it's explained in this other paper. So we also have this Frobenius norm of the weight matrices of our neural network. And in the denominator, we have this T, this threshold value again. And of course, we have our sample complexity here as well, the number of unlabeled data points. Finally, we have this other term, which depends on the probability of failure, and P, which is the number of layers of our neural network. And then, of course, we have N again. So as I said, you can plug these into the population guarantees that we gave before, and it will result in finite sample guarantees. I'm going to show the bound for the self-training case. It's very complicated, so I won't go into it in too much detail. And honestly, the authors only give like a little bit of intuition for this. They present most of this in the appendix, so it's not actually even part of the main paper itself. So this is what it looks like. You can see that it's very complicated. Essentially, the main thing that the authors note regarding these finite sample guarantees is the sample complexity that they're able to get. So they compare it with some previous work that used unparameterized models. And these unparameterized models required sample complexities that were exponential in dimension. So, the results here are significantly better than that. And the second thing to note is that, just briefly, the authors are able to provide a lower bound on this robust margin term, this thresholded robust margin term, And essentially what they're able to find is that this scales inversely with the Lipschitzness of the model. So those are just the only two things that the authors really pointed out here. I think the main point is that they're able to get at least a non-exponential sample complexities. So finally, we'll talk briefly about.
Sorry, Matt.
Yeah, go ahead.
To the previous slide. So this is interesting. So is the reason that they were able to get they were able to improve upon this exponential complexity because of the expansion assumption? That the main reason why they can get a better result?
I guess I'm not familiar enough with the unparameterized models and why those were exponential in dimension to make like a comparison. It seemed to me like if you just kind of follow their steps, you just naturally result in this kind of bound. I mean, we see these kind of bounds that come out of the Rademacher complexity typically, right? Or like this is kind of what we want to see. So based on what we've seen in class, it almost seems natural that if you perform the analysis this way, you're going to get that bound. But like I said, I'm not familiar with the unparameterized cases, so I can't really like do a comparison there.
I see. Okay, yeah, that's fine. So yeah, leave it offline.
So yeah, we'll talk about the two experiments that they ran. The first experiment they present is essentially run with the intent of showing expansion in like a real data set. So, you know, again, I won't go into too much detail here, but essentially what they show is that the set of mistakes of their trained classifier, which we can determine based on its performance on the validation data. We can determine the size of that roughly by the performance on the validation data. Has a neighborhood that includes about 20% of the probability mass of the overall distribution. So what they're trying to show is that this set of mistakes expands into something that's larger than the set of mistakes. So what they do is they sample a bunch of points from a GAN, or they sample a bunch of images from a GAN conditioned on some specific classes, and then they apply an adversarial perturbation to these samples until the label is flipped to something that's incorrect. And so they find that about 20% of these perturbed examples lie within some L2 distance of the original examples. And so if we pick this L2 distance as our definition of the transformation set, then what we can say is that they're neighbors of each other. The perturbed samples are neighbors of original samples. However, the original samples are correct and the other ones are mistakes. And so because we know the size of the mistakes, the probability mass of the set of mistakes via the validation set, then essentially what we can say is that this set of mistakes expands into a neighborhood that's roughly 20% of the distribution. So, I mean, essentially they're able to show some evidence of expansion for one specific set of a data set, or a distribution. But you know, when we require expansion, we require expansion on all subsets under a certain probability mass. So they're really only showing like one case of expansion here. So it's you know, arguably like kind of weak. But of course it's difficult to show this underlying population property. So at least they were able to show something here.
Yeah, so I think maybe this is an interesting open question. So for example, if we only assume a weaker version of expansion, where let's say that for 90% of the subsets, right, they satisfy these expansion, but maybe for 10% they don't. Are these like, do you still get these like nice guarantees, or do you now go into the exponential complexity region, right? So it seems like a very natural question to think about how robust are these guarantees under this expansion assumption.
Yeah, it might be interesting to perform sort of a similar analysis with these different assumptions and see what the result is. So the second experiment that I performed was the intent of validating the objectives that we gave, specifically the intent of validating the objective we gave for the self-training setting. So essentially what they do here is they apply practical techniques that are somehow analogous to the terms we see in the objective. I think Tien talked about this or asked me about this last time. And so what they do is they just pick these practical techniques that are analogous to the terms we see in the objective. And then they rerun this experiment by adding one of these components each time. And then they compare the results. So essentially what they're trying to see is like some improvement of results as they add each of these components. So they start out with just the pseudo labels. And then they add this VAT loss, which I guess is some adversarial robustness regularization. And so this is supposed to be analogous to our notion of input consistency. And it's similar to these other papers that have come out recently that have shown good results with input consistency regularization. And then they add this AMO algorithm, which I guess they've presented in another paper, which regularizes their notion of robust all layer margin. And they essentially say that it's supposed to help like generalization. And then they add this thing that they're calling min-ent, which essentially allows the training algorithm to ignore some fraction of the pseudo labels if it results in an improvement of the cross entropy loss. And so what they say is that they add this because the previous components serve to encourage robustness only for examples that fit the pseudo label. But if we allow the algorithm to ignore some pseudo labels, then it can help encourage robustness for the incorrectly pseudo labeled examples as well. And then finally, they just remove the pseudo labels to see what the decrease in performance looks like. And so I've debated whether to show the actual results here, but they're pretty self-explanatory, or they're pretty like obvious, I guess, when you look at it. So essentially, they're able to show that when they add each of these components, that they see some improvement. And then, of course, when they remove the pseudo labels, it decreases performance dramatically. And so the authors argue that because each of these components adds or improves the results, that this gives some amount of justification for the terms that they use in the objective function. So finally, I took a look on Open Review at there's like a small handful of reviews there, just to see what they were talking about with regard to the paper. They had a lot of writing, but as far as like key feedback, they actually only had a few points. The first is that they tended to agree that the assumptions that the authors use are pretty novel and pretty intuitive. They make a lot of sense. However, they all agreed that it's pretty difficult to show evidence of expansion in real data sets. And so that was one drawback. I would say this was sort of one of the main concerns. And of course, the reviewers mentioned this, but also conceded that it's just difficult to show, right? So they would have liked to see it, but they at least conceded that it's
so actually, right? So for example, if we can manage to extend the result to this weaker version where we only require this expansion to hold, let's say, for 90% of the subsets, then we can now verify this, because to make sure 90% of the subsets satisfy, we just have to sample a bunch and make sure over 90% of them satisfy this assumption, right? So I think that would be like pretty easy to verify. Again, I suspect that there's something more technical down there.
Mm-hmm.
Yeah, but
and then finally, a couple of reviewers questioned how to implement these objectives, as we've talked about a couple of times. One reviewer notes that population-based loss isn't really used in practice because it's just too expensive to estimate. And so, the authors replied to these concerns and were able to give some examples, like we saw in the experiment, of techniques that are sort of analogous to the terms that we saw in the loss. And what they also mentioned, of course, is that they hope that the results of this paper encourage some additional development of practical losses that can be used well, in practice. So that's pretty much it as far as the presentation goes. I guess, does anyone have